introduction. So Robert Griffin is a research scientist at IHMC. He has been doing a lot of cool works on Atlas and other humanoid robots, and I think they have developed a new Nadia robot that we are very much looking forward to hearing from them. Robert, the stage is yours.
Great, thank you very much for the introduction, and thank you to the organizers for putting on this workshop. I'm sorry I couldn't be there in person, but so thank you again for also being very flexible, for helping me switch spots and be able to still present remotely. So the work I'm going to be showing is I'm really thankful for Ye for kind of teeing up some of the conversation pieces that I'm going to have here. That's pretty fantastic that me moving my talk ended up probably working better for me. But I'm going to be talking a lot about some of the work that we've been doing here recently on the development of these kind of push recovery algorithms, as well as thinking a little bit more towards this agile locomotion, specifically thinking about angular momentum. So kind of to start things off so we've been developing this robot Nadia, and I'll just do 1 or 2 slides on it here in a moment, but this is kind of the video of us doing some of the different push recoveries on it, where you can see, I'm just applying these external disturbances, and it's really exciting for me, having worked with Atlas, Valkyrie, and then some robots previous to that were not capable of doing this at all. So having a robot that's actually physically capable of doing push recovery has been enjoyable to work with. Just quickly, Nadia is our new humanoid robot that we've kind of developed in-house in conjunction with Boardwalk Robotics, as well as some unofficial collaborators like at IIT. It's kind of a mix between hydraulic and electric actuators, where we have the standard 6 degree of freedom legs, where 5 of them are hydraulic and 1 is electric, and then a 3 degree of freedom spine, and then 7 degree of freedom arms. In each of these, you can see that we have these custom planetary drives that kind of make up the pelvis and are 1 of the degrees of freedom of the spine. We also have these commercial off-the-shelf motors, which are just T-motors for the existing version of the arms. We're hoping to improve those here relatively soon so that they can be more powerful and actually, pick up useful things. And then we have these Moog integrated smart actuators that are powering the legs and the spine so there's 12 of these hydraulic actuators on the robot right now. We're hoping to replace these in the near future with some of our own custom ones, simply because these came in 1 size. Kind of note as well is that we designed the robot to be made out of carbon fiber for most of it, are going to be the shells. And the idea here was a couple of things. One, so that you could, kind of fully enclose all of the actuation and wiring and everything like that, so that you can protect the robot, so that things like, the springs breaking when the legs collide, like what Ye was talking about, we can avoid, but also so that we can start moving towards this kind of multi-contact locomotion. Because I think that in the types of places that we want to send our robots, that's what we're likely to see a lot of. A colleague of mine is there this week, Sylvain Bertrand, who actually gave a talk in another workshop here recently. I had a picture of him on the previous slide. If you want to ask him lots of questions about the hardware, he will tell you that he doesn't know, but he's the person to ask. Kind of the thing that frames a lot of our investigation has been this idea of developing these legged robots to go through complex urban environments. So whether this is things like disaster response or firefighting, there's these environments that are typically going to be designed around people that we want our robots to be able to go into. So it's not simply just this walk down the hallway problem. It's really being able to perform kind of precise locomotion while also being very robust. And you can kind of see an example of this. Here's a former colleague of mine exploring a typical disaster zone, which is a garage, where he has to, squeeze between tight places, precisely put his feet on surfaces in the environment, then be able to do things like walk over, in this case, a rug, but you could think of it as a balance beam in order to just get an object of interest, in this case, a tennis racket. And these are things that not only do we not think, but many other forms of robot would be capable of doing, but many other control methodologies. This requires a very specific approach where the robot can pick these footholds and pick these contacts in order to actually accomplish this kind of locomotion. And that's driven a lot of our work in the past. Here you can see Atlas going up and down the cinder blocks. In this case, we're telling it go to the top platform, then go to the bottom, and it's kind of modeling the environment and then actually planning these contacts itself in order to get over there, because that's what we want these robots to be able to do, is walk, move, and interact in these kind of constrained environments. We want them to be able to be able to precisely navigate the world around them when needed. And to that, we have these kind of general requirements that we've put together for what we want out of a walking controller that drives a lot of the work that we do. One is we want them to be usable in a wide variety of terrains. I know that there's definitely a lot of merit to having custom controllers for custom settings, and I think that sequential composition, like what Ye is talking about, is one of the definite ways to achieve that. But then you have like 80 controllers that you have to tune based on these different environments, and we're really focused on trying to get the minimal set of controllers that can go over the maximal set of terrains. We also really want to be able to characterize what the controller is doing. If I'm debugging this robot, it did something wrong, or if I'm trying to figure out, what it was trying to do, I really want to be able to say what it's trying to do there at any given time. And additionally, I want to be able to command, go in and actually say, oh, well, you were doing this. I actually want you to do this, and actually provide those kind of inputs to the robot and have it execute it in real time. And, this is actually one of the reasons that we've historically kind of avoided model predictive control and reinforcement learning, is because it's often fairly challenging to gain intuition as to what the output of these controllers are doing, or how to easily change what they're doing, because it's solving some potentially wild cost function that if you add a cost or add a constraint, it could have pretty far-reaching ramifications further on down the line. That's not to say that those methods aren't worth investigating. I definitely think that that's the future, but that's been kind of why we've stuck with the approach that we're using, which is mainly to do reduced order models. If I think about walking as just a simple inverted pendulum, that covers a lot of things. I can code a lot of locomotion based on these points. So here you can kind of just see the standard center of pressure, centroidal moment, pivot point, which are just driving this divergent component of motion or capture point. And you can also see, it's just linear, and you can get a really good vertical plot of everything that's going on, and you can understand exactly what the robot's doing. And you can also, use these to recursively calculate a trajectory based on a desired set of footholds. And then you can execute this online. And this is exactly what we were doing with Atlas and the other videos. We've applied it to Nadia, and it starts to work pretty well. It's not quite as dynamic as what we would like. I think that, particularly as you start trying to shorten the double support phase, which I think is something that's a big difference between a lot of these classical humanoid ZMP style walking locomotion and dynamic natural locomotion, is that ZMP has a long double support phase, natural walking does not. And we start to run into problems using these classical approaches, but we think that it does look pretty good, and the robot can move pretty quickly in a lot of different directions. And it's also extendable to these kind of multi-contact scenarios. So I know I showed Atlas doing it, but I have to plug some of our other work that Duncan Calvert's going to be presenting tomorrow, where we're actually, kind of tying in real-time perception and real-time footstep planning so that the robot can, reactively plan as it's moving over these environments. But this doesn't really talk about any kind of robustness. From here, I've mainly just said, well, if you have a set of footholds, how you would track them and plan to achieve them. And as you can see at the end of this, occasionally it will mess up, and you need to do things like foothold adjustment. To that end, we've continued to use capture regions. If you're not familiar with capture regions, it's basically just the set of points at which you can put your foot in order to come to a stop, if you're talking about the one-step capture region. So, here you can see that on the left, if I'm just thinking about a really basic line. It's not wanting to play again. Let's see. If I think about just a basic line, as the dynamics evolve, you can see where the center of mass ends up. And then you can extend this easily into 2 dimensions, into this kind of convex state. You can also look at expanding this to multi-step capture regions. So, you know, if I don't necessarily want to come to a stop in a single step, but I know that it will kind of decay towards this capturability. One of the big issues that we've seen, and I think that Ye touched on this a little bit in his talk recently, was this doesn't actually take into account crossover steps at all. Or the fact that in reality, the base of support, you can't just arbitrarily step. You have this area where you can't put your foot really. In this case, I've indicated it by the red area. And if I think about, you know, the way that you typically calculate these capture regions is you assume that you can step anywhere within a certain distance. And if I actually look at how this affects the expansion of these capture regions by adding this kind of reachability area, which is this big blue polygon that I have on the left, you can see as I expand my capture regions, these regions here, I don't get any additional, or I don't get much additional capturability towards the inside because I can't do those crossovers. I can't actually reach them. So adding that to the area in which the robot, you know, if I add that to the reachable set of the robot, I can then expand it pretty considerably. But, you know, just applying this as is, one of the things that we notice is that you have to be very particular about it. So it works, but you have to be very particular about when you push the robot if you want to make a good video like this. Otherwise, it just falls over. And I think part of that, if you think about it, is again because of this transfer duration. So, you know, I can tell the robot, oh, if you're under a disturbance, step more quickly. And I can then, but one of the things that you really want to do is if you have this long transfer duration, it's effectively the same thing as having a much slower swing. So you can see here that vastly reduces the amount of capturability that I actually have. So instead, by basically treating the capture point as a phase variable, instead you can compute what the current duration through transfer should be in order to kind of minimize this amount of feedback. And so then, you know, if I have my capture point, you know, near the back of the trailing foot, I'm basically at the start of transfer. Or if it's near the front of the foot that's about to be my support foot, I'm basically at the end of transfer and I might as well initialize the next step. So you can actually do this to kind of compute that swing speed up. And that's one of the big things that we did in order to, see if I can mute this. In order to get this robot to step much more robustly, was give it the ability to more or less skip the transfer step. You know, if you look at the video previously at the beginning, you can push the robot pretty much whenever. Here's a good example, and it will skip the transfer phase as needed. But one of the things that we typically see on robots is that you're walking in full support and not in. I don't know. Those didn't export as videos. They're walking in full support, whereas humans don't really need this kind of a full support area. So here would be a video of these people walking over rocks, where you can kind of see there's pretty much always just points of contact. It's not like they're always having this kind of full foothold, which you typically see in a human. If you've ever seen kind of a monkey walk, let me see, this should be playing. I'm not 100% sure why it's not. But you can actually imagine kind of this gibbon or a tightrope walker walking where they have this big long balance beam that they're able to hold. They're pretty much just using that kind of angular momentum to regulate those interactions. We can actually go back to the simple models again to understand this more fully. So if I look at you can actually see here's an example with Atlas. All we're doing is we've told the robot, oh, you're standing on a line, and we're allowing the CMP to leave the foot, which is the same thing as the robot getting these, the force vector not pointing through the center of mass anymore. So generating significant angular momentum. And you can kind of see how this directly relates to the torque about the center of mass. So it's really just using that angular momentum for the control of the robot. And we can apply this actually to the platform, walking over these kind of angled center blocks where the robot's then able to kind of infer what the ground contact conditions are. And then it can actually walk across these kind of center blocks. And this is from a handful of years ago. And you know, one of the big takeaways is, okay, yeah, angular momentum is useful for controlling balance. We've thought about this a lot with this kind of angular momentum, or the linear inverted pendulum model with a flywheel. And one of the underlying assumptions of this is that we don't have any angular momentum just occurring naturally. All of it is this kind of feedback control that you're doing. But even if you're not talking about these kind of dynamic motions that Ye was showing, where mini cheetahs jumping, once you start having non-massless legs, where, you know, on Nadia, we have very heavy legs of the robot. The center of mass is actually around the center of the hip pitch. So it's, I think, below the pelvis. You have considerable angular momentum just walking. So here's kind of a plot on the left. You can see we're generating a lot just by having the robot walk not that quickly. So to kind of address this, one of the things that we started exploring was the use of this three potato model, which is a pretty basic idea. It's been used before, where you just have this center of mass position, and then is your main potato, and then you have a potato for each foot, or they're just these point masses or particle masses. And then you can kind of compute from walking what this required angular momentum is. So this isn't quite to the same extent as using this dynamic idea of having full inverse kinematics or a full body model for model predictive control, but it is kind of towards that, where you have your trajectories and you're able to plan using these simplified models. One of the problems, though, is that it's good. That model is good, but it's not perfect. You can see it largely captures the trends. So I have my black or red lines here in the middle, but the actual measured value, the measured angular momentum in blue. This is some work that's being investigated by James Foster at IHMC. But, you know, this prediction value isn't really as accurate as we'd like it to be. So to address that, you can actually introduce machine learning, which is great. You know, I'm happy that we can actually use it somewhere in our stack. And in this case, what we're doing is actually learning residual models. So we still have our entire reference value from the three potato model, and we're learning the residual values to try and drive that three potato model towards the actual whole body angular momentum model that you can calculate in real time. So training this doesn't take very much time. It only takes about 2 minutes, and then you can run it, infer on it, obviously in real time. And using it, it looks fantastic. And so you can actually then use these angular momentum trajectories to directly calculate a modified capture point trajectory, which, if you're interested in that, I'd refer you to a lot of work done previously by colleagues like Johannes Engelsberger. And it works pretty well on hardware. We think that it's going to enable us to do more dynamic locomotion. We haven't yet fully been able to investigate that, but that's one of the kind of the areas that we're looking at going. However, none of this looks very natural. You know, if I compare the robot on the left to the human on the right, you know, I've kind of taken snapshots of these same phases. Both the steps are a lot shorter, the knees are much more bent, you know, the arms are in some fixed position as the robot's walking. We really want to move towards having kind of a straighter knee during stride, as well as introducing some arm swing. And, you know, while encoding arm swing as a heuristic where you just, you know, can say, oh yeah, swing the arms while it walks is an option, we're looking to try and come up with a more model-based approach towards that. And to that end, this is actually, I appreciate the plug again by Ye. So we worked on trying to think about this, what is the angular analog to a center of mass? So, you know, he talked about you can have this angular excursion value where you're basically integrating forward in time what the angular momentum of the system is to try and compute that value, but that's going to drift because it is this non-integrable function intrinsically because it's a non-holonomic system. And then also, you know, you can say that things like arm swing emerge from centroidal angular momentum, but if you're just relying on that, again, that's a velocity control. It's not a position control. So we're trying to figure out a way of actually coming up with this angular center of mass. And to do that, you know, so one of the reasons that we want to do that is because I think it was of note that you can't really use just velocity control for angular momentum because it's going to drift, as well as it's not a very smooth signal when you start thinking about it in a real actual feedback control setting. But you need to have some kind of concept of it. If you start looking at some of these videos that have been generated previously of these really dynamic motions, this concept of having an angular momentum or an angular positional state is kind of baked into having stable solutions that can be done. So to that end, this work done by a colleague of Yu-Ming Chen, who's a PhD student with Michael Poza over at UPenn. We looked at this way of actually encoding the orientation of the robot. And we basically said that we wanted to have some rotation from the base, which is typically the pelvis, to this angular center of mass that then minimizes the angular velocity of the system. And you know, we can then just define it as a quaternion. And you know, you can compute the angular momentum of the system pretty standard, where you have your rotation at this angular center of mass, then you have the angular velocity of the base in the world, and then you have the angular velocity of the angular center of mass relative to the base, right? If you actually decompose this, you can see that you have the rotation is a function of whatever your orientation is, and then your you then have Jacobians that are a function of position, and then it's just a linear function of the joint velocity. So the idea is to actually fit this rotation matrix to basis vectors. So we can actually set up an optimization where you then randomly sample the configurations of the robot, and you can define some function that is this rotational center of mass to get your quaternion that then minimizes this system using an optimization to drive the derivative to look like angular momentum. And this again also converges in about 2 minutes, and it gives you this angular center of mass state. And when you apply this on the robot, you can get pretty good walking. You can see here, you have the robot standing in an upright fashion with the legs pretty straight. And then we're getting this arm swing just kind of emerging naturally. One of the things that I think is an issue with it is that, because you know, it's not quite as smooth as we would like, but I think that partly has to do with the shape of the underlying trajectories when it comes to things like the swing leg, how we don't have really great angular momentum profile there. But we think that, you know, there's a lot of other ways that you can apply this, because you're basically now, you have some angular state variable, and you can do whether it be constraints in order so that the robot can naturally adjust its posture during manipulation tasks, or crouching, or just feedback control, so that you then reduce the number of these kind of feedback controllers that you typically pass into a whole body control module, and you just have your natural posture function of the robot that you're going towards. We're also looking, as I said, we haven't really made much progress on this, but we're looking at trying to go into more dynamic locomotion, specifically looking at angular momentum, just using simple models on Nadia, because now we have a robot that's capable of doing it, which is pretty exciting. So this is just kind of thinking about using the classical, using the concept of the angular linear inverted pendulum introduced by Yukai Gong in the last few years, where it's encoding the linear and angular momentum into a single state, and then using that to calculate where to step. So that's one of the elements going into this. We're also looking, towards running. This is, again, if you want to talk more with Sylvan about this, I'd recommend doing so. So we're interested in having Nadia run here in the near future, building off some work by Johannes. We've had a lot of different performers on this project, as well as thanking our funding sources of NASA, ONR, and the DAC. And I can't forget our partners at IIT, Haloti, and Moog. And then this all takes a huge team to build the hardware, write the software, do all the algorithms. So much thanks to all of them. That I'd like to mention, we are hiring. We're looking for people at all different levels, from interns and PhD students to full research scientists. We're really focused on controls and mechanical engineers at the moment. With that, I'd like to open up the floor for any questions.
Okay, thanks a lot, Robert. That was really interesting. Steve, is there any question from audience?
Not yet.
Okay, I can start with one. So Robert, so you showed a lot of walking motions and recently some running motions. So how would you deal with multi-contact where you cannot maybe use the notion of capture point, or maybe you need to modify that such that you're able to do that? How do you think about those kind of problems?
So we've been looking into that a little bit, where one of the ideas that we're trying to do is encode a lot of those decision making into a higher level of actually having the human direct some of it. So the human can pick exactly where the robot steps, which is similar to what we've done with Atlas in the past. And I think that that's a good, first initial step towards it, because I think that there's just a lot that we don't know. I do think that more than likely, because you're having to deal with a lot more actuation constraints in the arms than you would typically have to deal with in walking, it's probably going to require some kind of nonlinear model predictive controller. Just because, in walking, you can basically assume, oh yeah, my legs are going to be strong enough to exert the forces that I need them to exert to walk across the room. And in Nadia, we get 900 Newton meters of torque at the ankles, which is preposterous. So we don't have to think about it at all. But with the arms, that's one of the hardest parts, I think. There's a lot you can do with this kind of projected support area on the ground, where you can expand the support polygon to consider the multi-contact, but that doesn't really take into account the actuation limitations. I think that there's something that you can look at when it comes to Romeo Orsolino's work of that actuation aware wrench polytope or something. I can't exactly remember the name of it, but he'd done some good work that we've been playing with a little bit, and coupling that with kind of a virtual reality interface where you can see the limitations of the capability of the robot to figure out what the reasonable contacts are for it to take in those kind of environments, which is kind of an answer, but not really an answer. And so.
Oh, we have a question here from, I think, Olivia.
Okay, yes. We are waiting for the question, Steve, right?
Can you, okay, you need to turn on the mic.
There's also a question in the chat. We can start with that.
Can you hear me?
Yes.
Yes.
Yeah, sorry. So just to make it short, congratulations for the talk and for the impressive integration with Nadia. So related with the robot and the hydraulic system, could you elaborate a little bit on the difficulty of doing torque control with the system? So for example, what is the bandwidth of the actuators?
Yeah, so that's something that we've struggled a lot with. As you probably know, hydraulics aren't the best force source or torque source, especially at lower forces. So I think the bandwidth, we've managed to get a pretty high bandwidth on them. I don't exactly know, but I think it's around 50 hertz, which we're pretty happy with. However, when we're asking for lower forces, like in swing, we have to primarily do a lot of acceleration integration and then treat it more as a velocity controller, which isn't ideal. I think partly that's a function of the fact that it's a two-stage valve in the piston itself. So you kind of have the, Moog did a really, really good job of trying to engineer that problem out. But I think that in general, just by the fact that you're having to flutter back and forth on the spool between the two ports in order to actually get the control around that force, it isn't ideal. The arms are pretty good because those are T motors. The hips are good. I don't exactly know the bandwidth of those, but we did a lot of work on modeling the cogging itself of the planetary drives in order to try and get it to be really smooth. And then the new arms that we're building are going to be significantly better than the existing ones. I'm really excited about those. And that's just feed forward modeling.
Okay, thank you very much.
Thanks a lot, Robert. There is also a question. Yeah, you have a question?
Sorry, can I have a real quick? Yeah, thanks,
yeah.
Robert, for this very nice presentation. I think we definitely should have more conversations offline. But I have a question on this this Angular center of mass, and can you share any thoughts like you have, like how this Angular center of mass representation is maybe close or maybe very different from the, let's say, just the torso orientation or the trunk orientation? I think a lot of people use to, I think, represent or a very simple way to represent the orientation. And maybe I think you talk about the running and how you see this Angular center of mass can maybe give some physical interpretation about the orientations of the robots. And yeah, do you have any insights on this?
Yeah, so I can tell you the biggest thing, one of the big differences is going to be when it comes to the interplay of the distal limbs. So if you're just pinning your angular state to the torso, if you then move the leg, it has no effect on the angular state of the system. But if your leg has any kind of inertia to it at all, you know, the more inertia that it has, the more moving that leg is going to affect the angular momentum of the system, which means that it should then also affect the integral of the angular momentum or the angular center of mass. And so that's one of the reasons why we kind of pursued this. So in the video that I show where the robot was kind of swinging its arms, we weren't telling it to do that. That was an emergent thing. We were telling it to move the legs. And then in order to regulate the angular center of mass to a 0 configuration, it had to move the arms based on the Jacobian. And I think that that's something that you'll see a lot as you start kind of adding additional constraints to the system, where you were to like move the arms, then it could pitch the torso in order to actually, you know, raise the arms up to counter that angular center of mass position. So it actually encodes that from kind of a positional state. And I think that you would get a lot of similar properties from that angular excursion if you were to initialize it at the correct value. But it's the fact that it's so dependent upon where you initialize it and then when you reinitialize it that I think is the nice thing that this angular center of mass avoids, because it's a positional function.
I see. So it's okay. I see. Okay. Yeah. And I mean, this angular excursion is sort of more like this path dependent, right? Like you might get different answers if you have start from different initial kind of position or configuration where you start to integrate things.